to the Simons Institute. My name is Peter Bartlett. I'm the Associate Director. Welcome to this Richard M. Karp Distinguished Lecture. Very happy to have you joining us. We established this series to celebrate the role of Simons Institute founding director Dick Karp in theoretical computer science. And the series features visionary leaders in TCS and in neighboring areas, and it's geared towards a broad scientific audience. We're grateful to the many contributors to the Richard M. Karp Fund who've made the series possible. I'm really delighted to welcome our speaker today, Uri Feige. Uri is Professor of Computer Science and Applied Mathematics at the Weizmann Institute of Science. He's had research positions at Princeton University, IBM TJ Watson Research Center, and at the Microsoft Theory Group, Microsoft Research Theory Group. And he continues to serve as a visiting researcher at Microsoft Research in Herzliya. His main research interests are algorithms, computational complexity, and algorithmic game theory. He's won many awards and prizes, including the 2001 Gödel Prize for the PCP theorem and its applications in hardness of approximation. Very happy to have Uri here today. His talk's entitled Finding Large Cliques in Random and Semi-Random Graphs. Join me in welcoming Uri Feige.
So thank you. It's a pleasure to be here. So the talk is finding large cliques in random and semi-random graphs. So let's start from the clique problem. So the input is a graph with n vertices and an integer parameter k. And the question is whether this graph contains a clique of size k. So as we all know, a clique is a complete subgraph that has all the edges. So this is a clique of size 4. And the k-clique problem is NP-complete, as we all know. So the topic of this talk is the maximum clique problem in random graphs. So the model that we have is the GNP R-Reni random graph model, where every edge, there are n vertices, and every edge is present independently with probability p. In our talk, we limit the discussion to p equals half. So every edge is present with probability half. In these graphs, it's well known that the largest clique with overwhelming probability over the choice of graph is of size roughly 2 log n. Logarithms here are in base 2. And the simple greedy algorithm finds a clique of size roughly log n, just 1 log n. And the simple algorithm is you pick a random vertex, remove all its non-neighbors, and then recurs on the graph that remains. So in each step, you gain a vertex and lose half the vertices. So you get log n vertices in the clique. And I hope I got the year right, but in 1976, apparently, okay, Dick Karp asked whether there's some value of epsilon greater than 0, and a polynomial time algorithm that with high probability finds a clique of size larger than log n, 1 plus epsilon log n, in a random graph. So this is a long-standing open problem. It's still open today. So I really have no solutions to tell you about. So I'll just tell you about research that this question led to, or research that is related to this question. So the outline of the talk, so again, this is the problem that we will be considering. So one aspect of the talk would be how do you approach such a question, like what kind of algorithms you would be the first ones to try. So I'll discuss these algorithms. Okay, we'll get to them. They don't work. So then we'll do what we usually do in computer science. We'll slightly change the question and try to answer related questions. And also there we'll see that we don't always know the answers. So the things I'll present would not necessarily be in historical order. They're more in some logical order. And of course, I will mention some references, but many additional references will be omitted. Okay. So a first approach to design an algorithm to find an object that you know exists is to see how you prove that this object exists, and then see if the proof can be made constructive. So we claim that in a random graph, the largest clique is of the size 2 log n. So how do we know that? And maybe if we see how the proof goes, from this we can find also an algorithm that would find the clique. So the proof is by a probabilistic argument. So the expected number of cliques of size k is exactly, so this is an exact, you have look at all possible subsets of size k of the vertices, that's n choose k, and each one is a clique with, if all edges are present, this happens with probability 2 to the minus k choose 2. And if you do the computation, if k is larger than 2 log n, up to lower order terms that I ignore here, the expectation is less than 1, so we don't expect to have any clique there of that size. And if k is smaller than 2 log n, the expectation is greater than 1. This by itself does not imply that there's a clique there, but since the variance can be shown to also be small, so that the standard deviation is smaller than the expectation, then we know that with high probability there is a clique there. So that's how we know that there are cliques of size 2 log n, roughly 2 log n in random graphs. The question is, can we make this probabilistic argument constructive? Can we change it into an algorithm? So there are probabilistic arguments that can be made constructive. A well-known example is the Lovász-Loka lemma. But for many other probabilistic arguments, we don't know how to translate them into algorithms. And this is one of these arguments, because essentially all that it says is that if you pick a random set of k vertices, the probability that they are a clique is 2 to the minus k choose 2. So the algorithm that you try based on this argument would just be sampling random subsets of k vertices until you get a clique. But this would take time 2 to the k choose 2, 2 to the k square roughly. And this is too slow. This is not polynomial time for our interest, for our value of k of interest here. So this would not work. Okay, another approach that you should automatically try is to try to see if maybe the problem is easy even on worst case instances. So our goal is to efficiently find a clique of size 1 plus epsilon log n in a random graph that we know has a clique of size 2 log n. The question is, maybe we can, in every graph that has a clique of size 2 log n, efficiently find a clique of size 1 plus epsilon log n. Possibly we can do it. And we know that this problem is probably not NP hard, because even by exhaustive search, you can solve it in time n to the order log n. And for NP hard problems, we don't expect there to be algorithms of this running time. So the problem is probably not NP hard. So can we solve it in polynomial time? So here are some examples of related problems, and this relates to the area of fixed parameter tractability. So here are other objects that you can find in a graph more efficiently. So if you are looking for a simple path, k vertices that form a path and do not repeat themselves, then this can be found in time polynomially in n times 2 to the order k, something exponential in k, but the k is not in the exponent of the n, it's in the exponent of the 2. Likewise, a vertex cover can be found in this time, or also a clique of size n minus k instead of a clique of size k can also be found in this time. So in fact, if you think about it, this is essentially the vertex cover problem in disguise. So maybe also clique can be found in this running time. And if it can be found in this running time, if we substitute the order log n for k, this is polynomial running time. So let's see what algorithms we know for finding cliques, and is there any hope of having an algorithm with such a running time? So exhaustive search, going over all subsets of size k, is time roughly n to the k. Here's something better that we can do. We can list all maximal cliques in a graph in polynomial time per clique. So if there are, let's say, only polynomially many maximal cliques, a clique is maximal if it cannot be enlarged by adding any vertex. If there are only polynomially many maximal cliques, we can list all of them in polynomial time and find the maximum clique. For our random graph, the number of maximal cliques, it's not too difficult to show. It's something like n to the half log n. So we can find the maximum clique in time n to the half log n. The maximum clique is of size 2 log n. Another algorithm that is useful for finding cliques is fast matrix multiplication. It doesn't give a big advantage, but it's very important in the sense that it shows us that there are kind of ideas of how to find cliques that seem to not be related to cliques somehow. So a graph G, if we look at its adjacency matrix, so if it has a triangle, so a triangle is a clique of size 3, so then its trace, if you raise the matrix A to the power of 3 and look at the diagonal, then in the trace you have a non-zero entry. And a non-zero entry corresponds to a triangle. And this you can detect by doing fast matrix multiplication of A with itself. And this takes time faster than n cubed. So it's n to the omega, where omega is the current constant for matrix multiplication. So it's faster than n cubed. And this can be generalized to finding cliques of size k in time roughly n to the omega over 3, which is smaller than 1, times k. So this shows that there are like some kind of non-trivial algorithms for finding cliques. But we have some evidence that there are that clique is not fixed parameter tractable in the sense that it cannot be solved in time, let's say polynomial in n times some function of k. So one assumption that we can use is the well-known exponential time hypothesis. And this hypothesis says that solving 3-SAT requires time really exponential in n. It's a stronger version of p not equals to np, which just says that the polynomial time does not suffice. And the same hypothesis says that the same holds for max clique. Like these problems are interreducible to each other. So if cliques of size log n can be found in polynomial time, it can be shown that then max clique can be solved in time roughly 2 to the, let's say, square root n, and this would contradict the exponential time hypothesis. I'll sketch a proof in the next slide. There are other evidence that clique is not fixed parameter tractable. There is a notion of a hierarchy of, let's say, hardness for various problems, and this clique the clique problem is complete for the first level of this hierarchy, which serves as evidence that it's cannot be solved in time polynomial in n times some function of k. So let me just briefly sketch the proof. So that's a relatively easy proof. Why, if you can find cliques of size log n in polynomial time, this would contradict the exponential time hypothesis. So this is a rather simple argument. So assume we have an algorithm that finds cliques of size, let's say, n over 2. So as the exponential time hypothesis says that finding cliques of size n over 2 should take time exponential in n. How would we solve this problem? If we have a graph on n vertices in which we want to find a clique of size n over 2, we'll construct a new graph on many more vertices, n to the order square root n vertices. This is the graph G prime. Its vertices are subsets of vertices of size square root n in the original graph. And two such vertices are connected by an edge if together they form a clique of size 2 square root n. So they have to be disjoint sets of vertices that together form a clique of size 2 square root n. So it's quite easy to see that this graph would have a clique of size half square root n if and only if the original graph had a clique of size n over 2, because it have half square root n times square root n is n over 2. Okay, so if in this original graph, now half square root n is log of the size of the new graph. So if you can solve the task of finding log size clique in the new graph in time polynomial in the size of the new graph, this would be time 2 to the order of square root n log n and would refute the exponential time hypothesis. Okay, so we have evidence that it's difficult in the worst case to find cliques of size log n. Another thing we might try to do is approximation algorithms. So let's denote by omega of G the size of the maximum clique in a graph G. And we can ask, is there some approximation ratio rho, which is larger than half, such that in every graph G, not just a random graph, a clique of size at least rho times the maximum size can be found in polynomial time. Because if there is such an algorithm, all we're asking in our case is to find a clique slightly larger than half the maximum size. When in 1976 this question was open, by now using the PCP theorem and related work, we know that for any rho greater than 0, the problem remains NP-hard. And using approach like I showed in the previous slide, this also shows that even if you try to approximate the size of the maximum clique when the cliques are small, like order log n, it's still you get the ETH hardness according to the exponential time hypothesis. So again, we don't expect to have algorithms like this. So the summary so far is that the question was, is there some epsilon in a polynomial time algorithm that with high probability finds a clique of size 1 plus epsilon times log n in a random graph? What we've seen, if we assume the exponential time hypothesis, which maybe, again, in 1976, people maybe were not willing to assume it, I don't know, by now we are willing to assume it, then such an algorithm, if it exists, will have to make use of the fact that the input graph is random. It cannot work for worst case graphs. We tried to use the fact that the input graph is random by inspecting the proof of how we know that random graphs have large cliques, or not so large, of size order log n. But this argument also does not translate into any useful algorithm. So we need some fresh ideas here. Any questions so far? Okay. Okay, so let's re-examine the algorithm that finds cliques of size roughly log n and see if we understand it really and understand its limitations. So here's the simple algorithm. You pick a vertex at random, put it in your clique, and remove all its non-neighbors, and repeat. This is the algorithm that I described. And roughly in each step, the size of the graph decreases by a factor of 2, so you find a clique of size log n. The running time of this algorithm is really order n, even though the graph has, to describe the graph, you need n squared bits to describe which between every pair of vertices, if you have an edge, really the running time is only order n, because in the first step, you pick a random vertex, look at its neighbors, so that's n steps. And then in the next step, you have only a graph of size n over 2, and so on. So you have a geometric series, and the running time is order n. If you're willing to spend more time, you can have a marginal improvement, but not significant. Instead of picking an arbitrary vertex, a random vertex, in each step, pick the vertex of highest degree, because then you have the most vertices remaining. The change in the result is very marginal, insignificant, and the running time increases to n squared just to find the vertex of highest degree, just for the first step. Okay, so it's probably not worth the problem, bother to do it. Yeah. So here's an improved algorithm, which is somewhat better. So it's like the previous algorithm, but we stop early. So we repeat the process until n prime vertices remain, and I chose n prime to be 2 to the power of square root 2 log n. Okay, n prime. So we select each time a random vertex, remove its non-neighbors, but we stop when the number of vertices that remain is n prime. And at this point, we switch to a different algorithm. So when n prime vertices remain, the size of the largest clique there is 2 log of n prime. So for what I chose, it's 2 square root 2 log n. And now we switch to the algorithm of enumerating all cliques in this graph. So the running time of that algorithm was n prime to the half log n prime, which is order n, still linear in n. And we find the maximum clique in this subgraph that remain. So instead of extracting from this subgraph that remain a clique of only size log n prime, as the greedy algorithm would do, we extract a clique of size 2 log n prime. So using this, we gain a log n prime. So we find the clique of size log n plus log n prime, which gains us a square root 2 log n low order term. So this algorithm uses a paradigm that for this talk, I'll call it the max in neighborhood paradigm. Okay. So what does the algorithm really do? You find a random clique K1 of size little k1, let's say by the greedy algorithm. This was the first step of the algorithm. And we choose the value of this K1 such that the neighborhood of it is sufficiently small so that you have enough resources to find in it the maximum clique. So you find the maximum in this neighborhood, the maximum clique in the neighborhood, that's K2, and you return the union of the two. Okay, so this is the algorithmic paradigm used by these particular algorithms. So if your resources are order n time, I showed that you can find a clique of size log n plus square root of 2 log n. If you allow yourself polynomial time, you don't gain much. You just, in the second order term, instead of 2 square, just the constant changes in front of the square root log n. So this is the paradigm that we use. So we can ask ourselves, for a given amount of resources, is this max in neighborhood paradigm optimal? Let's say up to negligible terms, or can you improve upon it? We would like to answer this question when the resource is the running time, but we don't know enough about computation. We don't understand computation well enough to answer this question. For example, if we would prove that it's optimal, we prove that P is different than NP. So we are far away from showing that it is optimal. But this is a computational problem. What can computation do? We can change it to an easier problem, which is an informational problem. So this is what we'll do now. And this informational problem, we may be able to answer. So we look at a certain probe model from a paper with also with Prasad. We started studying it, and there were additional work. So here, the situation is different. We have no limit on computation time, but we don't know the graph. We can probe entries in its adjacency matrix and get information about the graph, and we are limited in how much information we can get. So a probe, you ask for a pair ij, 2 vertices, and in reply, you are told if there's an edge between them or not. And we pay only for these probes. We don't pay for computation, and we need to find a clique as large as possible. So if you had n choose 2 probes, you could probe the whole adjacency matrix and find the maximum clique because there's no bound on your computation time. And the question is, what happens if you have only linear number of probes, order n, not order n squared? So certainly you can find a clique of size at least log n plus this square root of 2 log n because we had a linear time algorithm that found it. So this linear time algorithm could not look at more than linear number of edges in the graph. So this is certainly something that you can do. And the question is, can you do better? So what would you do, let's say, if you had to do all the probes in parallel? Okay, no adaptivity at all. Okay, so you can take a set of square root n vertices, ask about all the edges inside, learn the complete graph, the whole graph on these t vertices. This graph has a size, as the clique of size 2 log of the size of t, so it's 2 log square root n, which is log n. So you'd find a clique of size log n in 1 round. What happens if you allow yourself more and more adaptivity, more rounds? Then we saw that in 1 round you can find log n, clique of size log n. In 2 rounds, we'll not show this. You can find a clique of 4/3 log n. In 3 rounds. Yeah, so in the second round, the questions can depend on the answers from the first round. In 3 rounds, almost 3 log n up to low order terms, 3/2 log n. And if you don't bound the number of rounds, we know how to find cliques of size 3/2 log n. All these algorithms, I'll show the one for 3 rounds in a minute. All these algorithms are based on the same max in neighborhood paradigm that I explained before. All the rounds, except for the last one, find a random clique K1 and a set T of square root n neighbors. And in the last round, you query this set T and find there a clique of size log n. And this is what you return, the cliques that you found in the first round union with this last clique. For example, the one round algorithm, really what it does, it finds the empty, like the K1 is empty, there's nothing there, and just finds K2. So let's see the 3-round algorithm first in a slide, then in pictures. Yes. I'll get to it. Yeah, okay. Okay, so let me sketch the algorithm for 3 rounds and also show it later in a picture. So in round 1, you find some arbitrary clique, a random clique of size half log n. How do you do that? We know that you can find a clique of size log n in 1 round, so you can certainly take just half log n of the vertices. Now in the second round, you try to find a neighborhood which vertices are connected to all vertices of your clique. So since you have only order n probes in the second round, and the clique is already of size half log n, so you take a set of n over log n vertices and query all the edges between this set S and your clique K1, and find within this set S the set of a set T, which are those vertices that are neighbors of all of K1. And the size of T is going to be something like square root n over log n with high probability. And then you ask about all pairs inside T and find the maximum clique in T. So if you do the computation, the maximum clique in T is of size log n minus a lower order term. And altogether, you found the clique of size 3/2 log n minus order log n. Let's do it just again in a picture. So first you find this clique K1 of size half log n in your graph. Then you take a set S such that you have enough probes available to ask about all edges between S and K1. So S has to be of size roughly n over log n. And you ask about all these edges. This is in the second round. In the output of the second round, you discover the set T, all the vertices which are neighbors of all of K1. And then in the third round, you ask about all edges inside T and find the maximum clique there, which is K2. And you return the union of the two. So it's also this maxi neighborhood paradigm where in round 3, you find the maximum clique in T. So we can ask whether in the computational model that we started with, we did not know if the maximum neighborhood paradigm is optimal, but we can ask, is it optimal in the probe model? If your limitation is the number of probes, not the computation time. So for one round, we know that it's optimal, that you cannot find something larger than log n, a clique larger than log n. For 2 rounds, we also know that it's optimal, that you cannot find something, a clique larger than 4/3 log n. For 3 rounds, we don't know. We have an upper bound of 1.6 instead of 1.5, 1.62. And if you allow an arbitrary number of rounds, we know how to find the cliques of size 3/2 log n, and the upper bound is roughly 1.7 log n, the known upper bound. So we don't have tight bounds. So let me just explain the upper bound for the 1 round case, because it's the simplest of all upper bounds. They get much more complicated as you add rounds, but it contains an ingredient that is used in all proofs. Okay, so let's say here, let's call the number of probes Q. Doesn't have to be n. The same argument works regardless of the value of Q. If we will substitute for Q the value of n, we'd get this upper bound of log n. Okay, so what do we know? We know that our algorithm returned the cliques of size k, so it must have probed all the edges of this clique. Otherwise, how would it know that it is a clique? Okay, if enough that it did not probe one edge, and with probability half, it's already not a clique. Okay, so it probed all the edges of the clique. If it probed all the edges of the clique, it also probed a maximum matching inside this clique. So the clique is of size k, it has a matching of size k/2. So k/2 edges that touch all the vertices. Let's, for simplicity, assume that k is even. So this matching is incident with all vertices of the clique. So given the probe pattern, this you select non-adaptively. In the first round, you select what edges you're going to probe. you know that if you're going to return a clique, k/2 of the edges of your probe will touch all the vertices of the clique. So there are only q choose k/2 possibilities of which are the vertices of the clique. And then each such set of k vertices is a clique with probability 2 to the minus k/2. So if this product, for the algorithm to succeed, it must be that this product is larger than 1. And if you plug in values for q, you get tight bounds. So for 1 round, you get the tight bounds. For 2 rounds, the argument is considerably more complicated. And for 3 rounds, we don't know how to make it tight. Okay. So summary of the probe model. So maxi neighborhood is the best algorithm we know for finding cliques in random graphs. When the limiting resource is running time, we have no idea how to prove that it is optimal. But when the limiting resource is the number of probes, we can prove its optimality if there's limited adaptivity up to 2 rounds. And for more rounds, we have non-trivial bounds. So there's hope maybe that we'll be able to determine if it's optimal or not. Ideally, we'll find that it's not optimal and get new ideas of how to also use algorithms in the computational setting. But we don't know. Yes. So back to bounded computation time. So we said that the size of the maximum clique, omega g, is likely to be 2 log n. But for the given input graph that you have, you don't know if it's 2 log n really. It can be any size. It's a random graph. Who knows what the coin tosses gave? So we discussed algorithms that for most random graphs efficiently find a clique of size log n, and hence they certify that the size of the maximum clique is at least log n. You can ask about refutation. For what value of k do we know that there's no clique larger than k? Like, how can you efficiently certify that there's no clique larger than k? This is like a Cohen-P statement, that there's no solution. So how do we do that? So here we look at a variation on the adjacency matrix of the graph. So I'll call this matrix the A of G. And for a graph, it's a symmetric n by n matrix where it's indexed the rows and columns by the vertices of the graph. And along the diagonal, we put 1s. And whenever there's an edge, if there's an edge between vertex I and j, we put 1. That's like the adjacency matrix. And if there's no edge, we put -1 instead of 0, which we put in the adjacency matrix. And if we have a clique of k by k clique in the graph, a k clique, then it will give a combinatorial block of all 1. So let me show it in a picture. So let's say this is our graph, a very simple graph with 4 vertices. And this is the matrix that we construct. So the diagonal is all 1. Whenever there's an edge, let's say between vertex 1 and 2, so the second entry in the first row is 1. And when there's no edge, let's say between vertex 3 and 4, so the fourth entry in the third row is -1. Okay, so that's the matrix. And if I look at any clique, let's say the triangle, it forms a block, a combinatorial square block of all 1s. Okay, combinatorial in the sense that it doesn't have to be consecutive. After rearranging the rows and columns, it becomes a block. Okay. So let's now go to spectral graph theory, which is very useful here. So this deals with eigenvalues of matrices associated with graphs. So this matrix here is one of these matrices. And this is useful algorithmically, spectral graph theory, because eigenvalues are correlated with some graph properties that are NP-hard. For example, we show, okay, we'll get there. Yet eigenvalues can be computed in polynomial time. So sometimes by computing eigenvalues, you learn something which otherwise is difficult to learn about the graph. So here's the fact that you can prove using Rayleigh quotients. I will not go over the proof. That if a symmetric matrix like our matrix AG has a k by k block of all 1s, then necessarily the largest eigenvalue of the symmetric matrix is at least k. That's not difficult to prove it. Consequently, since we said that this matrix AG has a block, a k by k block of all 1 if there's a clique of size k, it means that the largest eigenvalue of this matrix is at least as large as the maximum clique in the graph. Now we have a random graph, and a lot is known about eigenvalues of random graphs. So we know that if we take a random graph like G½ that we are using here and construct this matrix AG, with overwhelming probability, its largest eigenvalue is going to be roughly 2 square root n. Okay? So using this, we can certify that the input graph that we have does not have a clique larger than 2 square root n. We compute the largest eigenvalue. It's going to be 2 square root n, and we know from before that that's an upper bound on the size of the maximum clique. Okay, so we can ask, can we do better than this? So here's an improved upper bound by using convex programming. So again, we are going to construct a matrix from the graph, but we're not going to specify all entries. Some entries will optimize over them. So we'll have the matrix M. It's going to be an n by n symmetric matrix, also indexed by the vertices. The rows and the columns are indexed by the vertices of the graph. And we want to minimize its maximum eigenvalue subject to the following constraints. Along the diagonal, we put all 1s. And whenever there's an edge, we put a 1. So we maintain the property that there's a block of all 1s. If there's a clique of size k, there's a block of all 1s of size k. This property we maintain, and all other entries are free. You can do whatever you want with them. And you solve a convex problem that will find what values to put there so as to minimize the largest eigenvalue. So this can be computed, so it's a convex problem, and in fact, it can be computed using semi-definite programming. So a relatively easy type of convex, let's say, programming. So here's an example. Let's say this was our graph and the corresponding matrix AG that we had before. What changes now is that the entries that used to be -1, now I leave them free. Okay, the algorithm can choose whatever it wants to put them in order to minimize the largest eigenvalue. Okay, so this quantity is very much related to the Lovász theta function. So we'll refer to this value, lambda1 of this matrix M, as theta bar of G. So not theta of G. Why? Because it's really the complement of the theta function of Lovász, for those who know of this function. So the Lovász theta function has many, many formulations. And this is one of them for the edge complement of G, for the complement graph. So we'll call it theta bar, this quantity. And for every graph, we have that this theta bar is larger, at least as large as the largest clique, because there's this block of all 1s that limits how much we can reduce the maximum eigenvalue. In the theta function, where it was originally defined, it was for the complement graph, so it was larger than the largest independent set. But we are with theta bar here. And we know that it's smaller, not larger than the largest eigenvalue of this matrix AG, because we can minimize. Where we put the question marks, we can put whatever we want, and we minimize lambda1. So we're only improving. So it's a tighter upper bound on omega G than the first eigenvalue of AG is. Okay. So let's see a picture. So this is a plot made by Vadim Greenberg. So what do we see here in this plot? So each point is a random graph generated with 50 vertices. That's each point. So we have many points here. And for each point, the x coordinates says what the value like of the theta function is, what the semi-definite program gives. Whereas the y-axis says what's the maximum eigenvalue of this matrix AG without any optimization. So what do we see in this picture? So we see that if we look at the maximum eigenvalue, it's between, let's say, 11.5 and 15. That's the range of value that you have. But if you look at the value of this theta function, you get better upper bounds. between 9 and 6 point something. So there's an improvement. There's something a bit strange about this picture. The points look scattered nicely, but there are these vertical lines here. So does anybody know what these vertical lines are? So remember that the theta function is an upper bound on the size of the maximum clique. In these graphs, the maximum clique was of size 9. If not for that, these points would have moved left. And here they were of size 8. And like here, these 2 points were of size 7. And apparently, there were a few graphs where the maximum clique was smaller than 6, probably 5. Okay, so we see that the theta function does a better job than the maximum eigenvalue. And in fact, in this graph, sometimes it really tells us what's the size of the maximum clique. So, yes.
So those really were the max.
I asked Vadim to check, I did not check.
But okay, with the point being for n equals 50, you can check it.
It's not so easy, but yeah, because if you run many simulations, you want to check all of them. But yeah, you can check it. Process. So if you think what algorithm you'd use, maybe the one of listing all the cliques. Okay, so what do we know? So despite the nice success that we had for graphs of size 50, this was an artifact of checking it on size 50, because the value of the theta function can be shown to be at least square root n for random graphs. So this Lovas already showed, and the later paper showed a weaker bound, but for GNP, not GNH. Okay, so, and the maximum clique was of size 2 log n, so this upper bound is not very good. We can strengthen this upper bound because it's a convex program. So we can build various hierarchies on top of this convex program, like there's the Shirali-Adams hierarchy, the Lovas-Schreiber hierarchy, sum of squares hierarchies. There are many hierarchies, ways, systematic ways of adding constraints. So what do we find? So if we usually go t levels up in these hierarchies, what they do is reduce the upper bound by a factor of 2 to the order t. But the running time that they use is something like n to the omega t. So you spend much more running time for each factor of 2. Let's say for each factor of 2 that you reduce, you spend a factor of n more time. So you cannot go beyond the constant t in the remaining polynomial time, and this is still omega of square root n. So this is does not seem to give us very much. And in fact, if you're willing to spend time n to the omega t, you don't need any of these hierarchies. There are simpler algorithms that would show that there are no cliques of size square root n divided by 2 to the t. You don't need a convex programming at all. Just branch and bound and eigenvalue computations would do it for you. Okay, so now to the last topic. So let's make now the problem easier, the one of finding a clique of size 1 plus epsilon log n. So we'll move to the planted model. So we'll generate first a graph like from GNH. Yes.
If you have time n to the thing, you can go closer to square root n to the constant to the minus 2 square root n. In the first model, you said that like to do something similar, you need this computation resources. So do you have an argument why here you need this computation time to go to square constant square root n?
That's what we know. So like there are various proofs showing, let's say, that particular hierarchies would not do better than this or something similar to that. Let's say for the Lovas-Schreiber hierarchy, we have exactly this picture. For the sum of squares hierarchy, approximately this picture. But we know for specific algorithms that they don't work. We don't have a proof. No. Okay. So here we're moving to the planted clique problem. So we start with just a random G and half graph, but we call it G prime because we're going to change it. And now we plant in it a clique of size k. What does it mean? We select k distinct vertices independently at random and add to G all missing edges between pairs of vertices. So this gives the graph G. And the goal is now in this graph where we planted another clique, maybe now it's easier to find a clique of size 1 plus epsilon log n. This is what we're trying to do. So for what values of k is it feasible? If k is equal to n, of course, you can do it easily because the whole graph is a clique. If k is equal to 1, it didn't help you all what we did here. So probably for some value at the middle, it should help you. Now, if k is larger than 2 log n, then with high probability k, in fact, the planted clique is the unique maximum clique, and then in the graph. And then you can also ask, can you find this unique maximum clique in polynomial time? So information is there. Can you find it in a computational way? So what are the known results? So one kind of rule of thumb, okay, it's not a theorem, that if you'd be able to find a clique of size 1 plus epsilon log n in the planted model, and k is large enough, then also you'd find the planted clique. Okay, these are essentially the same problem. Okay. So now what do we know about finding the planted clique? So there's another rule of thumb that it's essentially the values of k for which you can find the planted clique are those for which the refutation worked. That these problems are roughly the same. Okay, so there are many algorithms. We showed that refutation works when the size of the clique is constant times square root n. And there are many algorithms that would find the planted clique if this is its size. So there are spectral algorithms. We also saw spectral algorithms for refutation. One's based on the Lovász theta function. We also saw those for refutation. There are other algorithms like message passing algorithms that also can find the planted clique. When the size of the planted clique is little of square root n, we don't know anything. Okay, we don't know of any polynomial time algorithm. So have we made progress here? So we use some sophisticated algorithm to find the planted clique. So it seems that progress is not very great, because even if you take just the simple algorithm of picking the k vertices of highest degree, this already finds for you the planted clique when the size of the planted clique is slightly more than square root n times log n. So it's a very simple algorithm. A variation on it, working backwards, removing the vertices of lowest degree 1 by 1, iteratively, already finds the planted clique when the size of the planted clique is a constant times square root n. So algorithms that do not use any spectral graph theory or any convex programming or anything essentially perform as well as the best algorithms that we know. So it seems that we did not make much progress. So we can ask, what advantages do the more sophisticated algorithms offer us? So there are two answers. So one regarding the semi-definite programming-based algorithms, and perhaps also the spectral algorithms. This was not worked out, I think. They can certify that the clique that they return is indeed the largest in the input graph. Okay? So you don't just output a clique and say this is the planted clique. You also certify there's no larger clique there. And that's an advantage. The other kind of advantage comes when you look at what's known as semi-random models and the issue of robustness. Okay, so the planted clique model is a purely random model. The exact input distribution is known. In semi-random models, the adversary, there's some adversary, which typically is not computationally bounded, has partial control over the input distribution. So let me give two examples. There are others. One example would be a monotone adversary. So you planted a random clique in a graph, and then the adversary can inspect the graph and remove edges which are not inside the clique. Somehow it should make finding the clique easier in some sense, because it's somehow hinting to you that it cannot be that both these vertices are in the clique. It gives you hints. Okay. Another example would be the adversarial hidden clique. So the adversary can inspect the random graph G½ before planting the clique and decide where to plant the clique in the graph. Rather than choosing k vertices at random, the adversary chooses k vertices. That's another semi-random model. So do algorithms extend to semi-random models? So if we look at the monotone adversary, it easily fools many of the algorithms. So the degree-based algorithms the one that takes the largest degree vertices or the low degree removal are easily fooled by these algorithms. Spectral algorithms are fooled by these adversaries. Standard message passing algorithms are fooled. So in a sense, it tells us that these algorithms were overfitted to the particular distribution. If you change the distribution a little, they fail. But if you look at algorithms based on semi-definite programming on the lowest theta function, they are not fooled by this adversary. Okay, so in a sense, this shows that these algorithms are better, more robust. Why should we study semi-random models? So there are like two reasons. One is practical significance. It adds robustness to average case analysis. So algorithms that work for semi-random models cover a wider range of instances than those that just work for random models. And the other is theoretical convenience. Once we have a mixture of an adversary and randomness, because we have an adversary, there's a chance of proving hardness results. And for some of the semi-random models, we have NP hardness results that explain why we don't find algorithms. There's no random model in which we have an NP hardness result, but for semi-random models we have. So sometimes we know, like if we hit a wall, we know that it's really a wall. Okay, so let me end with, okay, so what have we seen? So the question was to find cliques of size 1 plus epsilon log n in a random graph. And there's really no significant progress on this problem in 45 years. We can ask an easier question, finding cliques of size 1 plus epsilon log n, not in random graphs, but graphs with a planted clique of much larger size. So in the G(n)(half)k model, there's only marginal progress over trivial algorithms. We only succeed when k is equal to square root n, and this can be done by really simple algorithms. And this is among the easiest examples of computation information gap, where like in terms of information, there's this huge clique inside that waits for you to find it, but we don't know how to find it. And like in a formal way, it's among the easiest problems because there are reductions from this problem to many other problems. And the most significant progress, in my opinion, that we have is in the area of robustness, that we have now algorithms that work not just in random models, but can work in semi-random models. So I'll end with two open questions, both on the same slide. Okay, so I mentioned the probe model, and I said that for 2 rounds, we know that the bounds that we have are optimal. So this was not exactly correct. If we allow not n probes to the graph, but n to the 3½ probes to the graph in 2 rounds, then the maxi neighborhood algorithm would find a clique of size. You can do the computation, 7/4 times log n, and we don't know if it's optimal. And you can wonder what's the difference between n to the 3½ probes and n probes. Why would, for one thing, version proving a lower bound, upper bound be easier than the other? If you start playing with it, you'll see, okay, or ask me later. And another problem that I find quite intriguing is the following semi-random model. So we ask, for example, what happens if an adversary plants a clique in a random graph and plants it wherever we want. There's the alternative question of, let's say the adversary chooses whatever graph he wants, okay? And now you plant in it, select k vertices at random and make them into a clique. And the question is, in this graph, can you find a clique of size k? You might not be able to find the planted clique because let's say you started with a graph that was a clique. Then obviously you wouldn't know which vertices are the planted clique. But like it seems obviously difficult, but I don't know how to show that this is a difficult problem. So we have an arbitrary graph, plant a random k clique in it. Can you find the clique of size k? Okay, so I'll end here.
Questions?
This is the hypothesis. This is the G(n)(half)k model. So we know it's doable when k is like order square root n. So when k is say sort of like little o square root n, if you make the hypothesis this is a hard problem, does it have any interesting consequences or?
Okay. So I myself not sure that I'm willing to make the hypothesis.
No, just as a.
But yes, there are various papers that make this assumption, and based on this, prove. Because like what really happens here? So the way people, I mean, this is the whole field of making hypotheses. We have a certain algorithms that we know, okay? Like let's say semi-definite programming, spectral, whatever. You find your favorite problem. You try all the algorithms that you know and you hit a barrier. You cannot improve over it. And then you can make the hypothesis that you hit a barrier because there's nothing else. Because really at a different density, let's say the problem is difficult. And then in a sense, you're saying these are all the algorithms that we know. There's no new algorithm to discover. And then from this, you can make reductions sometimes to other problems and say also there, we now understand why there's a barrier. So in a sense, like there's a systematic way of making up hypotheses and proving consequences. It's not always easy. Sometimes you need very clever reductions. But like all of them, I think, really say that the kind of algorithms that we know now are optimal. And if you make this assumption, you usually can have consequences. Yeah.
Yeah, can you give us some insight into why you believe this rule of thumb 1, that you can, if you can find 1 plus epsilon times log n size in the planted model? That you can
so here's some intuition why I would believe it. So let's say first that even without planting a clique, you can find cliques of size 1 plus epsilon log n. In this case, I don't make any claims because maybe the algorithm would just find cliques anyway, nothing to do with the planted. But suppose that finding cliques of 1 plus epsilon log n is difficult in random graphs. Once you do the planting, it becomes easy. So if it becomes easy, it must be that at least epsilon log n of the vertices came from the planted clique. Because otherwise, you just take your random graph, plant in it a clique where you know where it is, maybe of size k, find the clique of size 1 plus epsilon log n, and remove the vertices from your clique, from the planted clique there, so you find something larger than, let's say, 1 plus epsilon log n. So you know that, let's say, at least epsilon over 2 log n came from your clique. So once you know it, like you can guess which vertices they are. There are not so many possibilities. Out of log n to choose epsilon log n, that's not many possibilities, less than n, okay? And for each such guess, once you guess them, you remove all their non-neighbors and recurse. So if you do an algorithm like this, you'd be able to find the planted clique.
Cool, cheers, thanks.
Thanks for the talk. I was wondering whether it's looking at the Erdős-Rényi graph was like the most interesting one, or is there like similar results for different type of random graphs? Like, I don't know, geometry graphs or configuration models or whatever.
So I think it's interesting also to look at other graphs, and sometimes it's people have looked at it. Sometimes the reason people look at other graphs is because, let's say, if you're interested in social networks, people don't believe that Erdős-Rényi graphs capture their structure. But this kind of problem, the nice thing about it is that it's like simple to state, and you know that people tried everything on it. So like if you're looking for, a tough problem, it's nice to look at it. But if you're really looking at applications, then of course, it's interesting to look at other graphs. Yeah.
Last question, we'll take the others offline.
Yeah, thank you very much. So in your first endeavor to find max cliques, 1 plus epsilon log n in the G1/2, you said that, like, do we have any understanding of positive results for positive temperature? So like not just greedy methods, but like Metropolis chain, like do we know if it can reach log n plus square root log n? Or like, because I know the Jerome negative result, but I'm not aware of any. Like,
okay, so there were these negative results by Jerome. My feeling is that the algorithms that we know, like if you try to make gradual improvement, like there's something related to this overlap gap property or something like that. If you look at the cliques of size, let's say of a certain size, they don't tell you how to find cliques of larger size because most of them like are maxima in the sense once you reach sizes above log n. So it's very difficult to apply algorithms like they don't even tell you that in the vicinity there's a larger clique. So it's difficult to apply these things.
All right, join me in thanking Uri. Fascinating talk.